Okay, so in this video, I want to make a very short comment on the previous video in the following way. So if you remember, if we look at simply the indefinite integral, we had the problem of integrating x times x squared plus 1 to the 10th power dx. This was our main example. Now, the idea here was simply to rewrite the two terms in a different order as to see the substitution more easily. So we have x squared plus 1 to the 10 times x dx. And if you recall, the idea was because the derivative of x squared plus 1 was 2x, up to a multiple of 2 it is just x. This was a perfect problem for the following U-substitution. By making this substitution, this integral became essentially trivial, where we didn't have to take the 10th power of x squared plus 1 to expand the whole thing out, then multiply by x, and then integrate this very long polynomial with the power rule. This integral with this substitution basically became trivial. This is just to show you how sensitive problems of U-substitutions may be. You say, well, what if I just simply, in a sense, or I should say on the surface, makes this look simpler? What if I remove the x term? And if I just ask to integrate x squared plus 1 to the 10th power dx? And you might say, well, will a U-substitution work here? Well, let's try and find out. Of course, we could take the 10th power of x squared plus 1, multiply the whole thing out, and then use the power rule in each term. As we've said, we like to avoid this, if at all possible. But, if we let u be x squared plus 1, the derivative being up to a factor of 2 being x, but the x is missing. So it looks like, because the x is missing, the u-sub may not work. So let's try here, see if we're right on the money. So we let u be x squared plus 1. So replacing x squared plus 1 by u, we get u to the 10th power. And now what about dx? Well, again as before, u is a function of x being x squared plus 1. Differentiate u with respect to x, and you get 2x. Multiply by dx to the right, and you get that du is 2x dx. But if you notice, before it was quite nice because we could replace the x dx by simply 1/2 du. But now we don't have x dx, we have dx. So in the end we have to say, to isolate dx, we must divide by 2x, and so dx is 1 over 2x, bringing this over here, times du. But there is a problem. When you make a U-substitution, you have to replace everything in terms of the old variable, here being x, in terms of the new variable here being u. So you have to replace dx as a function of u only. What we have right now is dx is 1 over 2x du. Everything is fine except for the x. This cannot be an x, it must be a function of u. And if you go back, well, we can solve for x as a function of u, right? If x squared plus 1 is equal to u, subtract 1 on both sides, so x squared will be u minus 1. Take the square root on both sides, and x ends up being the square root of u minus 1. So now you have x as a function of u. But look at what's going to happen. Dx will be 1 over 2 times x, but as a function of u, x is the root of u minus 1, times du. And now you have replaced dx as a function of u only. Now we can make the substitution, and we're going to get our dx is 1 over 2 root of u minus 1 du. We can factor the 1/2, and you're going to be left with u to the 10 divided by the square root of u minus 1 du. And as always, when you make a substitution, you ask, is the new integral easier than the original one? And the answer is quite the opposite. How will you integrate this? You have u to the 10 over the square root of u minus 1. You're stuck here. You can't do this. So you see that these problems are very sensitive. With the x up front, the integral after making the u substitution becomes trivial. Removing the x gives us a new problem, and if we try and make a similar u substitution, the new problem we get is actually even harder than the original one. So here, all of our work gives us nothing. To integrate this, there's no shortcut. Because the x is missing, the u sub does not work, so you have to expand the 10th power of x squared plus 1. Once that's done, power rule in each term. There's no way around it here. So just to show you that u subs do work, and sometimes they are great, as in this example, but they are very sensitive. Just a slight change can completely destroy our u substitution.